Hi guys, it's Mr. Lees here doing the SQA Higher Mathematics paper from 2019, paper 2, and we're on question 11. A manufacturer of chocolates is launching a new product in a novelty shaped cardboard boxes. So you have a cuboid with a cuboid shaped tunnel through it, and you're given various dimensions. The height of the box is h, the top of the box is a square of side 3x, so that's 3x, so that's 3x as well, of course. And the end of the tunnel is a square of side x, so that's an x by x square there, okay? And the volume of the box is 2000 centimeters cubed. So part A, show that the total surface area, which they give you as A, of the box is given by 16x squared plus 4000 over x. So the first thing you realise, of course, is that formula for the area has nothing to do with h, so we need to eliminate h to begin with. So let's get to it then. So we're told that the volume of the box is 2000 cubic centimeters, so let's work it out. So the volume of the box is the volume of the cuboid, take away the volume of the tunnel. So the volume of the cuboid is 3x times 3x times h, take away, and the volume of the tunnel is x times h there. So we have 3x times h, take away x times h. 3x times 3x is 9x squared h, take away x squared h, that gives you 8x squared h being the volume of the box in this kind of algebraic expression there. But again, we're told that the volume is 2000, so set that equal to 2000, and we realise that h is 2000 over 8x squared. And we now have a calculator, of course, we can tidy this up. 2000 over 8 is just 250, so h is 250 over x squared. And as I've illustrated there, we will need this later. So let's continue with part A then, for the surface area of the box. So the surface area of the box is, well, what do we have here? Well, going back to the diagram, we have the area of the top, 3x times 3x, take away x squared, that is this area here, and we've got two of them there, we've got the top and the bottom. So we have the area of the top, take away the area of the tunnel, so that's 3x times 3x, take away x times x, so that gives you 9x squared, take away x squared, so this gives you 8x squared. So the area of the top is 8x squared there, your 9x squared, take away your x squared, so this bit here is 8x squared. You have to double it, of course, because you've got the same area down below, so that's going to give you your 16x squared. We now have the area of the four sides, and each one is 3x times h, and they're all the same. So we have 3x times h, and we have four of them. So 3x times 4 is 12x times h. That gives you 12xh. And don't forget, we have the surface area of the tunnel. Okay, the tunnel is 4 rectangles there. So each one is x times h. So it's x times h times 4, because there's 4 there. And so that's 4xh. So the total surface area is the top there, just get that into view there, 16x squared, plus the sides, 12xh, plus the tunnel, that gives you 16xh. So there we have 16x squared plus 16x, and we can now replace h with 250 over x squared that we got earlier on. So the surface area is 16x squared plus 16 times 250, 4000 x over x squared, just leaves an x at the bottom. So it's 16x squared plus 4000 over x. And then for part B, to minimise the cost of production, the surface area, the area of the box should be as small as possible. Find the minimum area here. So hopefully you're used to this type of question where we differentiate this function here and set it equal to 0. Okay, state what you're going for though. The maximum or minimums occur when dA by dx is equal to 0. So let's differentiate. 216 is 32, x to the power of 1. You can see that I've just moved that x up there to be x to the minus 1. So it's minus 4,000 x to the power of minus 2. Let me move it back downstairs there. It looks a bit better. We're now going to solve this. So that 4,000 over x squared gets moved over. The minus 4,000 over x squared gets moved over to be 4,000 over x squared. The x squared goes up to be x cubed, and we divide by 32. So x cubed is 4,000 over 32, which is 125. And the cube root of 125 is 5. So there we have it there. Now let's just show that 5 does in fact give a minimum. So we test the gradient, dA by dx, for numbers smaller than 5, equal to 5, and greater than 5. I've chosen 4, 5, and 6, of course. 4 gives you a negative gradient, 5, of course, gives you a 0 gradient, and 6 gives you a positive gradient. This, of course, corresponds to a minimum. So x equals 5 does indeed correspond to a minimum. And what is the area when x is equal to 5? Well, we have our formula for the area, 16 times 5 squared plus 4,000 over 5. Use your calculator, of course, and that ends up being 1,200 square centimetres. And there is your final answer.